Hello everyone, my name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Today I would like to explain about the mechanics of orthogonal cutting. This one is the outcome of this topic. Recall the importance of geometry of cutting tools and coolants and tool materials for the analysis of material behavior during machining process or manufacturing processes. So we'll see what is the mechanics of orthogonal cutting. This one, this is the workpiece. This is the shear surface. So this one is the workpiece. Through this shear surface, this one is the tool bit. Otherwise, you can see like this one. Tool bit. So the chip flows like this one. So then the angle, so this is the angle of gamma that shows the rake angle. You know this one. Otherwise, here also you can see this one is the rake angle with the rake surface of the cutting tool. Okay, so this one is the gamma shows the rake angle. So AB, this shows the shear surface. This is the cutting direction. So you can see this one is the uncut chip thickness represented by T1. So this one is the chip thickness after cutting. This represents the T2. So general geometry of machining process by single point cutting tool, you know this one. Okay, so in this direction we will see velocity of the shear velocity. So in this direction we will see the velocity of the cutting velocity VC. Here you see the velocity of the frictional force VF. So these are the velocities, different velocity, cutting velocity, shear velocity, and velocity of the chip or frictional velocity. You can see. So T1 and T2, T1 that shows the uncut chip thickness, and T2 that shows the chip thickness after cutting. You know this one. Okay. So then R is the ratio of uncut chip thickness by chip thickness. T1 by T2, it always less than 1 because after cutting the thickness of the chip will be increased. So T1 is always less than the T2. Okay. So T1 by T2 is less than 1. We can see 1 by R is nothing but the chip reduction coefficient. Okay, so there are some angles. This is the angle of shear angle. So this one is the rack angle. You know this one. Okay, so these are the different components. Okay, assumptions for the orthogonal cutting, single point cutting tool, orthogonal cutting. No contact at the flank. Here there is no contact because if there is any contact, rubbing occurs between the workpiece and the tool bit. Okay, so width of the chip remains constant. So you can see this is the width of the chip width. Otherwise, this is the you can see this is the width, workpiece width, like this one. This is the okay. If you consider this is the just like three-dimensional body, like this. Okay. So next to uniform cutting velocity. So C is uniform, not varying. We are assuming this one. Next to a continuous chip is produced. Continuous chip formation is there. We are assuming this one. Next to volumetric changes of the material. So during machining, so these are zero. Okay, there is no changes in the material during this. So these are the different assumptions in the orthogonal cutting tool. Okay, in this condition, you know that volume before cut is equal to volume after cut based upon this assumption. So we know that volume before cut up to volume after cut. Volume before cut means thickness, uncut chip thickness T1, width is same, that is B, length is L1. Okay, so you can take this is the L1, this one is the chip length is equal to L2. Okay, then L1 is equal to same T2 B into L2. Okay, so B width, so based upon the so width of the chip remains constant. Okay, so based upon this assumption, so B will be cancelled. Then so T1 by T2 is equal to L2 by L1. This is one ratio. Okay, so if you know the chip thickness ratio, you can find out the uh, length before cutting, after cutting also you can find out. So this is the ratio. One more thing is the velocities. Velocity in shear, along the shear, that is the shear velocity. Along the cutting direction, that is the cutting velocity. Along the chip, this is the frictional velocity. We'll see what is the relationship between. You know that continuity equation. So continuity equation is equal to A1 V1 is equal to A2 V2. So based upon this one, just you are taking this one, that is the so T1 area is equal to uncut chip thickness into width into volume, that is the velocity, not its volume, velocity. Velocity VC is equal to T2 after cutting, T2 width B, and velocity of the chip velocity means the frictional velocity. Then the B will be cancelled. Here also T1 by T2 is equal to VC by VF. Okay, so T1 by T2 is equal to VF by VC, not VF by VC. So this is the one more relationship, that is equal to VF by VC. Okay, so these are the relationship between the thickness and length of the chip before cut and after cut, and the thickness of the chip before cut and after cut, and velocities, frictional velocity and cutting velocities. So these are the relationship between the different parameters. By using this one, you can solve the different numericals, and you can find out the chip thickness or uncut chip thickness, or the velocity, cutting velocity, or the length of the chip also. Okay, so these are the parameters. Now you will find the angles also. If you know the rake angle, so rake angle is the that is the angle of the tool bit, so that will be given. By using this rake angle, we can find out the shear angle. Finding the shear angle is very important. So here we'll see what is the shear angle. So pi, what is pi or tan pi? We can find out this one. So in last class also I explained this one. Once again, I want to repeat that one. You can see this is the just basic diagram of single point cutting tool. Okay, so this one is the workpiece and cut chip thickness. Okay, this is the shear angle pi. This one is the rake angle alpha. This one is the tool. Okay, so Vf is the chip velocity or frictional velocity. Okay, so this is the shear velocity here, cutting velocity. So T1. Next to B is the width that we can assume that width of the chip remains constant. We know this one. So now we'll see the how to find out the shear angle pi. Okay, okay, here this is the same basic diagram. Just to this one is the shear surface AB, and we can extend the line from B to horizontal line. So which is passing through uh, cutting direction. Okay, so that meets that line at C. Okay, then ABC is the one triangle we will get. This is the angle phi, and AB is the one side or hypotenuse. This is the thickness of uncut chip. This one is the T1. So this is the one triangle. So another triangle you can see. This is the rack face or the tool face. Okay. So from point B to extend one line from point B to on the rack surface, then it meets that point D. So here one more triangle is there. Can one more triangle is there. So that is point D. Okay. So you know this one already. This is the reference to rack surface. That is the rack angle. You know this one. Okay. So then you know this one. So this is the this side and this reference line 90 degrees. This angle is equal to pi. So then this is the 90 minus pi. You know this one 90 minus pi. Okay. So here one more triangle is triangle ABD and the triangle ABC. There are two triangles. This one is the C. So both the triangle have the same hypotenuse. Hypotenuse is equal to AB. Okay. So by using this triangle, we can take the relationship, the first one, based upon the first triangle, triangle ABC. By using this triangle, this one, you can apply the hypotenuse. Otherwise, sine pi is equal to so opposite side thickness by angle hypotenuse AB. Then AB is equal to uh, T1 by sine pi. So this is the equation one you can take. Okay. So next, by using the another triangle. So the triangle is that is the ABD. Okay. ABD. So by using the ABD, so this is the angle, total angle is equal to 90 minus pi plus gamma. You can write like this one, 90 minus uh, pi minus gamma. So this is the okay angle, that angle. So this triangle angle, complete angle. So by using this one, you can directly apply the sine rule. So that is the so because this BD is equal to chip thickness, that is the T2. You know this one. Then sine 90 minus pi minus 5 minus gamma is equal to T2 by AB. Then AB is equal to T2 by cos pi minus alpha or gamma, anything. Okay, gamma is the that shows the or alpha or gamma, anything that shows the rack angle. So here we can see just so this is the AB. So this one is the cutting line. If you extend this one that touches this C, this width is equal to uncut chip thickness T1. This one is the tool face. Okay. So the angle between the reference line to tool face is is gamma or alpha, anything that is a rake angle. Rake angle. Okay. So next we can extend the line from B to B2 on the face, B2 on the face of the tool that touches the surface, that is D. Okay. So here two triangles are there. So one is ABC. So this is the one triangle. If this angle is equal to phi, you have to find out this phi. So this is the phi. This one is the AB. This is the C. The thickness is equal to uncut chip thickness. By using this triangle, if you apply this sine angle, sine phi is equal to opposite side, that is the thickness T1 by hypotenuse, that is the AB. Then AB is equal to T1 by sine phi. So this is the equation. So another triangle. So this is the triangle. Here, this is pi means, so this one is the 90 minus pi. 90 minus pi. So this is equal to gamma. Okay, or alpha or gamma, anything. So don't confuse this one. So alpha or gamma, you can represent any alphabet. So as a just a rake angle. Okay, then if you consider this triangle, so the triangle is equal to, if you consider this one, this is the AB. Okay, so this is the 90 degrees. No. AB. This is the 90 degrees. This one is the 90 degrees. So this angle is equal to, this 90 minus pi. So plus gamma. Okay. So it means 90 minus of pi minus gamma. You can write like this one. So then this is the D point. The BD is nothing but it is the T2, is the chip thickness. Okay. So then if you apply the sine rule here also, sine 90 minus of pi minus gamma is equal to, so I put in, so opposite side BD, so BD by AB. Okay. So AB, BD is nothing but T2, you can write. So then AB is equal to, here also sine 90 minus theta is equal to cos theta. This one you can write like this one also. T2 by cos pi minus gamma. So this is the equation 2. Okay. So then you can equal the equation 1 and equation 2. So the equation 1 is equal to, because this one is the AB, this one is the AB. So equation 1 is equal to equation 2. Okay. So then equation 1 is equal to T by sine theta, sine pi is equal to T2 by cos pi minus gamma. Okay. So this is the equation. Okay. Then T1 by T2, just to shift like this one, that is equal to sine pi by cos pi minus gamma. Okay. So otherwise T1 by T2 is nothing but chip thickness ratio, that is uncut chip thickness by chip thickness. Otherwise 1 by R is equal to T2 by T1. Okay. So you can write like this one, T2 by T1 is equal to, so cos pi minus gamma by sine pi. Okay. So T2 by T1 is nothing but 1 by R is equal to, 1 by R is equal to, so cos A minus B is equal to cos A cos B plus sin A sin B. So sin by sin pi. Okay. So then 1 by R is equal to cos pi by sin pi. So you can write like this one, cos gamma by sin pi by cos pi. This is the tan pi here. You can write like this. Okay. So plus sin pi by sin pi cancel, then we can here, so that is the sin gamma. Okay, so then you can write like this one. So here this is 1 by r. You can send this term to left hand side, then cos gamma by tan pi is equal to 1 by r sin gamma. Okay, so then you can reciprocate this one, otherwise so tan pi by cos gamma is equal to r. Okay, sorry. Okay, here, so this one, this is equal to, you can send like this one, uh, cos gamma by tan pi is equal to 1 minus r minus sin pi, sin gamma. Okay, here just, then you can simplify this one like this one, cos gamma by tan pi is equal to 1 minus r sin gamma by r. Okay, so then you require the tan pi. So tan pi you have to find out the shear angle. So shear angle is equal to, you can write like this one. Otherwise you can cross multiply this one. So that is equal to uh, tan pi of 1 minus r or sin gamma is equal to r cos gamma. Okay, so then tan pi is equal to, so then tan pi is equal to r cos gamma by 1 minus r sin gamma. So this is the formula, you have to remember this one. So that the final formula for this shear angle, so otherwise pi is equal to tan inverse of r cos gamma by 1 minus r sin 1 minus r sin gamma. If you know the thickness ratios, r value, chip thickness ratio T1 by T2, and the rake angle alpha, then you can find out the shear angle. So this is the shear angle. So you have to remember this one. So we will solve one numerical based upon this formula here. So in an orthogonal cutting of a mild steel component, if the rake angle and the rake angle of the tool is 10 degrees, so alpha or gamma anything you can take, gamma is equal to 10 degrees, it has been given. So next to shear angle also given, shear angle, so here directly shear angle is given, that is the pi is equal to 30 degrees. Okay, find the chip thickness ratio. You have to find out the r value. You know that formula. So tan pi is equal to r cos gamma by 1 minus r sin gamma. So r value is equal to, what is the r value? Then you have to find out the r value. Okay. So tan pi, tan 30, 1 by root 3, you know this one. Tan 30 degrees is equal to r cos gamma is equal to cos 10 degrees by 1 minus r sin 10 degrees. So we can simplify this one, tan 31 by root 3, and then cos 10 and sin 10, you can write the values by using the calculator. Then you will get the answer like this one. Okay, so here just I'm given the answers, you can refer this one. So here rake angle is represented by alpha, don't confuse this one. So tan pi is equal to, RC is nothing but R ratio, chip thickness ratios. RC is equal to cos alpha, alpha is equal to gamma is equal to rake angle. Okay. Rake angle. So by 1 minus RC sin alpha. So tan 30 is equal to RC cos 10 degrees by 1 minus RC 10 degrees. If you solve this one by using the calculator, you can find out the RC value, that RC or R is equal to 0.53. So this is the ratio of the chip thickness. So now we'll see the merchant theory. So because in the previous diagram we already discussed the chip thickness ratio T1 by T2 and the length of the chips L2 by L1 we already discussed. Okay. Next, velocities of cutting velocity, shear velocity, and frictional velocity. So here Vf by Vc. So cutting velocities. So all these things already discussed. So by using the merchant theory, you can identify the different forces which are in orthogonal cutting. So just like along cutting, so cutting force, you can see normal of this one, that is the tangential force Ft. Similarly, Fs is the shear force, and next F small f is the frictional force. We'll see how to find out these forces in the orthogonal cutting. So that can be, so it means these forces can be derived from the by using the merchant theory on orthogonal cutting. Okay, so to understand this or to use this merchant theory to find the different cutting forces in orthogonal cutting, we have to take some assumptions. So we'll see what are the different assumptions in orthogonal cutting. So first one, the tool is perfectly sharp. Okay, so there is no contact along the clearance and flank. So this is what this one is the tool, you know, this one. This one is the shear surface, the chip. This one is the cutting direction. This one is the workpiece. Okay, so there is no clearance. There is some clearance. So it means so there is no contact between the workpiece and the tool. Okay, so you can observe this one. Okay. The tool is perfectly sharp and there is no contact along the clearance and flank face. Next, the cutting edge is straight line. You can see this one, extending perpendicular to the direction of motion. Okay, generate a plane surface as the work moves past it one. Next, width of the tool is greater than the that of the workpiece. So that one is the assumption. Next, depth of cut is also constant, no variation in depth of cut. Next, work moves relative to the tool with uniform velocity. So that VC is uniform. You can take shear surface is plane and extending upwards from the cutting edges. You know that this is the shear surface. Fs shear surface AB. So this one how to construct this as a assumption. Next, chip does not flow either sides. It flows on the rack face of the tool also. Next, a continuous chip is produced without any built-up edges. There is no built-up edges. The continuous chip movement is there. So these are the assumptions. By using these assumptions, you can understand the different forces which are in orthogonal cutting operations. We'll see what are the different forces. Okay. So here you can see this is the merchant circle. So you know that block diagram, that is once again just I'm drawing this one. This is the uh, next shear surface. This one is the workpiece. This one is the workpiece. Tool is moving like this one. Tool bit. So this one is the chip movement. This one is the rack angle, alpha, gamma, anything. Here also, this is the reference lines. So reference lines to edge of the and face of the cutting tool, that is the alpha, gamma, the rack angle. You know this one. So here in this direction, this is the shear angle. You know this one. So in this direction we'll see cutting velocity. In this direction we'll see shear velocity. So in this direction we'll see this is the velocity of the friction. Okay. In the similar manner, force also acting in this direction. So that is the FC. Sorry. FC, cutting force. Okay. Similarly, in this direction, we'll see the uh, shear force. Okay. So with respect to the face surface, here we'll see the frictional force FC, the frictional force between the chip and the rack surface. So this one you can see. So different forces, mainly cutting force, the perpendicularity of this cutting force. So that is the FT, tangential force or thrust force, you can see. So you can see like this one. So then if this is the FC horizontal, vertical is the FT, then resultant is like this one. So consider this is the center point, the resultant is like this one. This is R. So it is represented by like this one. Okay. So FC is the cutting force and FT is the thrust force. The resultant is R. The angle here, that is the X. Okay, you can represent this is X. Now we'll see the resultant triangle of shear force. Shear force acting like this one. Okay. Shear triangle you can see like here. You can see here. This one is the relationship between the cutting force and the thrust force. This one is the resultant. Angle is equal to x. Then according to Pythagoras theorem, you know this one resultant is equal to side square into side square, or fc square plus ft square. Okay. So the tan x is equal to opposite side, opposite force ft by adjacent force. So that is the fc. So you have to remember this one. So next we will see the shear force like this one here. You can triangle this one. So this is the shear force. The normal shear force. This is the which is perpendicular to shear force. So that is the FSN. FSN is equal to normal shear force. Fs is the shear force. So the angle of this one is equal to pi. You know that too. That is a shear angle. So if you consider that triangle, the relationship between the triangle, you can understand like this one. Okay. The triangle is given like this one. Okay. See, the triangle is equal to like this. Okay. So this is the x, you know this one, which is related to cutting force, and this one is the pi, which is related to shear. So then according to this triangle, the triangle is equal to then tan x plus pi is equal to opposite side, that is fsn by adjacent side fs. Okay. So if you know the pi and x value, you can find out these values. Otherwise, if you know any one of these forces, you can find out the another forces. So by using these relationships, you can find out the unknown parameters, either angles or the forces also. We'll see one more triangle. So here resultant is same. That one you have to observe this one. Then the frictional force moving like this one. You can change the direction like here. Okay. So that is the frictional force. So this is the frictional uh, force. So the frictional force normal to the frictional force is the normal force N. Okay. Then the beta is the angle of the friction. You know this one, beta. So the angle between the normal force and the resultant, you know this one. So you know this is the rake angle. So if you this is the rake angle means this one also rake angle. Then this is the just you have to find out this angle also. That angle is equal to you can take so that this one. Okay. So because this is the x, this one is the gamma. Total is equal to 90. Okay. So otherwise, if you take this triangle, this is 90 degrees and this one is the beta, then this is equal to 90 minus beta. Okay, so by using this one, this angle x plus 90 minus beta plus gamma is equal to 90 degrees, total 90 degrees. Okay, so this is 90 degrees. Then the relationship between is equal to x plus gamma is equal to beta. It means if you know the x, or if you know the rake angle and the friction angle, then you can find out the x value. Okay, so these are the different triangles which are related to different forces. The first triangle related to cutting force, second one is the triangle related to shear force, and third angle related to frictional force. By using these triangles, we can find out the forces, and we can find out the angles. Okay, so by using this triangular method, you can identify this one. Otherwise, by using the merchant circle, we can find out the formula for the different forces. Next class, we'll discuss that one also. Okay, one more thing is that is the energy for cutting. You know that energy is nothing but force into velocity. So energy of cutting force into cutting velocity, VC. VC. So this is the used energy. Next, energy of the friction, wastage of the energy. So that is a frictional force Ff into velocity, frictional velocity. Okay. So then the percentage of lost means lost force by overall cutting forces Fc into Vc into 100. Then you can find out the useful work done, or power loss in the friction also. You can find out this one. Okay, you can understand this properly. We will see one more condition. What is that one? So if the rake angle is equal to 0, what will be happen? So this is the one more condition. Special cases, gamma is equal to 0, then automatically this value, this frictional force comes into vertically. So that is equal to thrust force, like this one. Ft, Ff and Ft both are same. So then the formula tan beta is equal to Ff by normal force, or Ft by Fc, frictional force, thrust force by cutting force. We can find out like this one. Okay, so next we'll see the stress and the strains. What is stresses, and what is the how to find out the strains also. So this one also very important. First we'll see the stress. We know that formula stress, tau s is equal to shear force Fs by shear plane area. Shear plane area which is related to shear. Okay, so we'll see what is shear plane area, then you can find out the shear stress. Okay, so here it is the just machining process by single point cutting tool, orthogonal cutting. You know this one. So the tool is moving like this one. Okay, so then this will be the shear area. How to find out the shear area? We'll see. You know this is the B, the width of the workpiece. Then this height, this is the T1 is nothing but uncut chip thickness. Okay, sorry. So this is T1 is the uncut chip thickness. You know this one. Okay. So this angle, you know this one, that is the pi. Angle is called pi. You know that angle is pi, and this one is the T1. Then this is the AB. Then you can find out the AB. If you know the AB side, then if you multiply with AB with B, you will get this total area. That is the shear area. So then you have to find out the AB value. So if you, for this one, you can take this triangle of AB, this one. Okay, this is T1, this is the pi. Okay, then AB, if you apply the sin pi is equal to T1 by hypotenuse AB. Okay, then AB is equal to T1 by sin pi. Okay. So this side AB is equal to T1 by sin pi. So then shear area AS is equal to AB into width is equal to B. Okay, so that's total area. It means so T1 by sine phi into width b. Okay, so this is the shear area. Then you can find out the shear stress. Shear stress obvious is equal to shear force by Fs by shear area T1b by sine pi. So this is the formula. Otherwise, Fs sine pi by T1b. So this is the formula. By using this formula, you can find out the shear stresses. Okay. Now you will see the strains. Strain, you know this one. This is the just effect of stresses, change in length with respect to original length. You know this one because in the due to this compression and shearing movement, the chip thickness is greater than the uncut chip thickness. You know this one. So cutting chip thickness will be increased. We'll see because of strain. We'll see that one also. Here you can see this one. Okay, so this is the original chip thickness. This length will be increased. You have to find out this one. Okay, shear strain is equal to, okay, here you can see, just I'm explaining this one. So this length, this changing length, you have to consider this one AC. Okay, so for this one, just you know this AC finding for this one. This is the pi angle, you know this one, and this is the cutting line, FC cutting line, you know this one. So you can draw the one more line, that is the which is parallel to cutting line, that is the AB. So if it is parallel lines, automatically this pi is equal to this pi. Okay, so that is equal. Then you can take here we can observe the two types of triangles. If you draw the line from B to line, shear line, okay, that is AC. So that means the D. Here we can see two triangles. One is the ABD, one triangle. Another triangle is equal to BDC. So for the both the triangles, one side is uniform, that is the vertical side. You know this one. Okay. Then you can see the angles. So here angle is equal to pi. Then this angle also pi. If you take this triangle ABD triangle, so this is the 90 degrees. This one is the pi. So then this triangle is equal to 90 minus pi. 90 minus pi. Okay. So because of this triangle, so here just we are assuming, so this is the triangle, this angle is equal to K1, this angle is equal to K2, just for finding of K1 and K2. If you know the K1 and K2, then you can find out the AC distance. So AC is nothing but strain rate. So that is the increased length. Okay, so then, so first we will take the ABD. So triangle ABD. So all the triangles, the sum of angles in a triangle is equal to 180. You know this one. This is the pi. The first one. This is the pi. You know this one. Next to this angle is equal to 90. This angle is equal to 90. This is nothing but K2. Okay, K2 is equal to 180. Then K2 is equal to 90 minus pi. 90 minus pi. So this is the 90 minus pi. You know this one. Next we have to find out this triangle. So this the triangle is equal to according to BDC. According to BDC triangle BDC. Okay. So this is 90 degrees. This one is the gamma. This one is the gamma. Then we have to find out. So here, so this angle is equal to 90. This angle is equal to 90. This one is the pi, means this is nothing but 90 minus pi. 90 minus pi. So 90 minus pi plus gamma, one angle. So 90 minus pi plus gamma, one angle, plus x1. This is the K1. This is the angle. You have to find out this one. So this angle is equal to 90. So that is the 90 degrees. So total sum of the angles is equal to 180. By simplifying this one, then minus gamma, 90 will be cancelled, minus pi plus alpha or gamma, anything. Okay, so rectangle. So plus k1. So then k1 is equal to pi minus alpha. So by using this relationship, you can find out the this length. So length of AD by using the ABD triangle. Next length of the BC by using the BDC triangles. Okay. Then we can find out the way why you can represent at this length. This complete length is equal to some y or pi. Okay. So y is equal to the first one is equal to so tan apply. If you apply the tan, so if you tan theta is equal to opposite side by hypotenuse. Opposite side, so tan pi. So first one triangle, tan pi is equal to this triangle. Tan pi is equal to opposite side BD by hypotenuse is equal to AD. Okay, you require the AD. So AD. Okay, so BD is the common term, then BD is equal to AD tan pi. Okay, AD tan pi. So similarly, if you take this triangle, then if you apply the angle, so what is the angle? Okay, so you can take this triangles, this angles. Okay, so it means this triangle. Okay, anything you can take this triangle or this complete triangle also. Otherwise, you can take this triangle. So according to this triangle, sine 90 minus 90 minus pi. So 90 minus pi is equal to AD by BD. You know that BD is equal to AD by sine 90 minus pi. Sine 90 minus pi means cos pi. Okay, this is the equation. Okay, so similarly, you can use this triangle. So that is the triangle is equal to 90 minus pi. So this triangle is equal to pi minus alpha. If you take that one, then you will get the one more relationship, that is the BD value. If you equal this one, then you can find out the here DC by sine pi minus alpha is get. Okay, alpha or gamma. So if you equal this one, if you equal this one, you have to find out the AD and BC values. Otherwise, so then you can value the final value is equal to y is equal to AD value and DC values. So by using this one, you can find out the y value. Y value is equal to tan 90 minus pi plus tan pi by pi minus alpha. Okay. So anyhow, you can take this one. Okay. So if you take the first triangle, you will get this value. This means AD is equal to this value. If you take another triangle, so that is the BD is equal to this value. Okay. So both of adding up both is equal to, that is the strain. So then you can rewrite like this one. Y is equal to cot pi plus tan pi minus alpha. Okay. Otherwise, tan pi minus alpha plus cot pi anything. So this is the strain value. Sorry, strain value. So this is the value. So you can understand this one. So by using the merchant circle, okay, when you can understand the different forces of cutting force and shear force and the frictional forces. Then tangents of this one, the Ft, Fsn, you can understand, and Fn also. So these forces. So we'll solve the relationship or formula for the Fc and Fs and Ft by using the merchant circle in next class. Thank you for listening this class. So by this class, you can understood, I think, what is shear area and the shear force also, and the strain also. What is the relationship between the chip thickness and the chip lengths and the velocities also. Okay, so thank you listening this class. We'll see further relationship between the forces in next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.